All right, here is the more stuff for reaction basics regarding intermediates. So we looked at a couple chemicals on ionic mechanisms. So in ionic reactions, we expect the mechanism going on through ionic intermediates, initiated by most of the time ionic compounds, and creating positive, negative ions as an intermediate. So we looked at the strong hydroxide is causing heterolytic cleavage, like pushing electron to positively charged potential Lewis acid, since hydroxide is acting as a Lewis base, and also causing bond break here, and planning to form a stable conjugate base as a product. We can think of a lot of other variations, having many different number of carbons as well, with the oxygen negative as a Lewis base. Also, you can think of various acids, such as HCl donating H plus as an acid, Lewis acid electrophile. Then that will attract all kinds of Lewis base, whether strong or weak. Some of them can be, something like water, or even some sort of alcohol. So these weak bases attracted to strong acid, the electrophile, and creating ionic intermediates like this, or from here the tertiary alcohol, expecting something like that, and then it keeps going on. We'll talk about that later. Or even weakly bound pi electrons in the double bond or triple bond. Triple bond has a two pi bonds. They also can act as a Lewis base and give an electron to the protons, and creating intermediates by forming the bonds like this, and continue by forming cationic intermediates as one of the ionic mechanism. But all of them, as you can see, you are forming or breaking a bond with the two electrons involved. However, it's not surprising in organic to see some of the neutral molecules, such as T-butyl chloride, is creating ions like carbocation and the chloride. Then they can cause reactions. Depends on the partners that you put in. This carbocation can attract some Lewis base, and the chloride can act as electron donors, like a silver or some strong Lewis acids, and continue the reaction. So again, to form this, what happened was to force the pair of electron moving from one side to the other side completely, and you will continue with ionic mechanism this way. So when you do ionic mechanism, we use the arrow with the arrowhead, usual arrowhead, and telling the electrons moving from the base, the electron pair, to the acid, the atom. If you learn molecular orbital later, the electron is actually going into the sigma star or pi star, some anti-bonding orbital that causing the bond break. Here also it's not lone pair, but you are moving this electron pair, so arrow starts from there and it is going to the electrophile atom. And also the sigma bond can move. Also in organic chemistry, it is common to do synthesis or reaction using radicals. Well, you can make the radicals using metals such as a sodium or lithium, because they have one electron on the valence shell. So when you react with say this organic compound, you can show arrow this way. You give one electron and you notice the arrowhead is like a fish hook, only one arrowhead, unlike the ionic mechanism where you see two arrowheads. Then in order to form a bond, you need two electrons. So when one electron is given, in organic arrow notation, you bring one of the two electrons in the bond, then you have two electrons and you're forming a bond right there, if you could. Then the other electrons moving either to hydrogen or the carbon. That's when you have to make a decision. Where do you give electron? So wherever it's more stable, you give electron, right? So if you think about the hydrogen and carbon, carbon's always more stable because it has more, first of all, more room, but also it's not easy for radical donor to give electron to the carbon. It's easier for the hydrogen because the hydrogens are on the surface. And there are more reasons, but when we touch upon the radical reactions, we'll get into the more detail. So for now, if the carbon is the target, you can think of this carbon versus, say, this carbon versus this carbon. Which one do you prefer? Then where would you put radical? If you have a radical on this carbon, that is a secondary radical, and on the methyls, that's a primary radical, and you have more stability on the secondary radical. So you rather prefer reacting with this hydrogen on the secondary carbon, so you can form more stable product, the secondary radical. So if you continue on this first original example, the electron went on to the carbon, and then the hydrogen and sodium try to share electron, but as you know, they can't, because the sodium actually is metal, not able to compete with hydrogen for electron, so they are forming ionic bond. The difference of the electronegativity is too great, so you end up forming sodium positive after losing electron to the hydrogen. Hydrogen becomes hydride with the two electrons, like lone pair. So you can stop here. As you can see, you created radical. If you give 1 mole of sodium, though, sodium, lithium, or those singly occupied valence shell atoms, you can think of further reactions. You have 1 electron here and there, then the carbon and the sodium can try to form a bond by sharing the electron. Then you bring sodium, carbon together head to head, but you know the electron again will be moving on to the carbon because it's a lot more electronegative, and you get the negative charge there and the positive charge there. Well, you can try this with the oxygen as well, not just the carbon. So say you have this compound, then you can imagine reaction trying to react with the hydrogen and giving electron to the oxygen. Homolytically, you break the bond. And you notice the arrow, right? To give a radical. So there again, you form sodium hydride, but you are forming methyl oxy radical right there. So you can form radical. This can cause a lot of radical chain reactions. But this can again go to one more step with the sodium or lithium kind, and you can create methoxide. This is one of the strong base we use in organic chemistry. Well, these can react with halides also. So when they come together, now you know this and this. So you can see lithium chloride as ionic compound, but this organic portion becomes radical. Of course, you can go one more time with 1 mole of lithium to make methyl lithium complex. And as you can see, the negative charge in this case will be on the carbon, so it is extremely basic. So it's almost, you know, as dangerous as its bomb. So you have to be careful when you deal with this. So you can generate relatively strong bases through this radical mechanism, but you can use these to react with other compounds by limiting the amount and supply of the metals. Well, you can have other type of radical initiator. Such as halogens, chlorine or bromine molecules. Starting with a neutral, you can heat up to give more kinetic energy, or you can give photon to promote electron from the sigma bond, in this case, to the sigma star, causing bond break. So here you also have a homolytic cleavage. You can imagine you have 2 electrons in the bond, so one goes to here, the other goes there. Very contradictory to the ionic mechanism. You can create 2 chlorine atom, which is the radical. Also, there are common radical initiators. R can be even hydrogen, or methyl group, or R can be anything. R can be hydrogen, isopropyl group, or it can be even carbonyl with a methyl group, or it can even be more complicated one. All depends on the polarity they want or the reactivity they want. You can choose from, but the general mechanism is about the same. By giving heat or light, all these lone pairs is one of the prime reason why you can break this bond easily. And having about the same electronegativity, it's also promoting better chance to have a homolytic cleavage. It's not necessary always, but it is one of the prime reason. So you can have a 2-alkoxy radical. If R was a hydrogen, then you are getting hydroxy radical, and so on. Then using these radicals formed, you can do follow-up radical reactions. There are more examples. You can have, in the polymerization reactions, you can commonly notice this type of initiator as well. Here, what happens is the nitrogen has double bond already, so if you break off this way, giving electron to the R group, and this way, you create two alkyl radical, then you create nitrogen gas evolving away and pushing the reaction forward more, so you end up getting radical initiator right there. Also, N-bromosuccinimide, NBS, it looks like this, has bromo group on the nitrogen. It's not necessarily symmetrical, but it is forming radical in this manner upon heating or irradiation with a proper wavelength. And there you have radical. You can do follow-up chain reactions. And sometimes you see oxygen molecule, the normal oxygen molecule in a certain condition can act as an initiator itself. The oxygen, as you know, has a 2 pi star orbital with single electrons in it. So you can consider oxygen almost like this, biradical. That's one of the prime reasons why food in the atmosphere go bad, due to the radical reaction caused by oxygen. And oxygen is also radical electron donor, but it can also accept the electron, so oxidizing other organic compounds such as food. All right, so I mentioned heat and the photon making radical, right? So like this, you have this. Even alkyl radical depends on the certain structural requirement, which you don't need to know yet. But here, if you give photon, you can actually, some cases, generate radical like this. And if you remember, if you heat up this alkyl halide, you normally get carbocation with a chloride. You go to ionic mechanism selectively. But there you need a tertiary or secondary carbocation structure to form this reaction product. However, for the radical, you need also a high degree or resonance carbon to form radical, but it's not always necessary. And more commonly though, photochemically, you can cause reactions, radical reactions, using these things. All the previous radical initiators, they can form radicals using light photochemically, right? Not only heating thermally, but this kind of chemicals, you cannot form radical easily by heating up. They're normally inert, and you have to give some photon to make them radical like this way. They only live short time and they try to go back if conditions allowing them. They can probably form other compounds, but temporarily you can create this transient radical intermediate, and you can do radical reactions with this. Also, sometimes unusually, but when you react two normal double bonds, neutral compound under photolysis, you can see two pieces come together by breaking pi bond, and you can see biradical, one for biradical formation, and you can think of the subsequent radical reactions from it. And all kinds of the neutral molecule under photolysis can cause radical reactions. Before we do extensive ionic mechanisms, most likely for the rest of the videos, let's give a little bit of insight to the radical reaction mechanisms. So the first step of the radical reaction will be, as you saw, you need to create radicals. So you can use one of those initiator, heat up, or photochemically you generate the radical. So initiation is the step you use non-radical compound and create radical. So you initiate. Then you can define some subsequent steps as a propagation step, or you can define them as a termination step. But I must tell you that these two are not coming in the order. They're happening all the time, except the very beginning of the reaction. So if you have a propagation step, that's when you have a radical reacting with non-radical. Say you have propane, the secondary hydrogen is more reactive than primary because it's more stable radical if you form. So you know how to draw arrow for this step. Radical, try to make a bond, and then you form a bond by donating one of the sigma electron, and then this goes to the carbon with a one arrowhead, and you form HCl. Then you form secondary carboradical. Then one other possible propagation step is using the formed radical of carbon. This can react with all kinds of things in the flask. Imagine all of them here, they're all in the same reaction flask. So this can react with this can react with that, this can react with this can react with this as well. So there are all kinds of reactions. But the propagation step, you need to only put the reaction that is using the radical to form a radical. So if you imagine this radical reacting with this radical, then as you can see, you're forming bond, so you end up making this by sharing these two electrons right there in the sigma bond. So it's not propagation, because in definition propagation is when you have a radical reacting and creates radical as a product. That's not the case. So although this step is happening while these things are running into each other to do propagation step, that's why I said earlier propagation and terminations are not in the sequence. So if they did that without knowing what they're doing, right, you define that as a termination step. So one of the other possible propagation step is when this react with the original chlorine, then you can draw arrow. Then you can notice the formation of this and chlorine. See, that's propagation, because you use the radical and you created radical. Then you can think of other propagation and other termination reactions, but using these two, if you add up these two, you can come up with a key overall reaction formula. So here you can cancel this, and then you can cancel this. So overall what happened is you had propane, let me push up a little bit, and you have them reacted with the Cl2 under light or heat, and you created chlorine and the HCl. So what happened here is actually remove the one of the hydrogens and you put the chlorine instead, so you have a radical substitution reaction. So substitution you did right here. Okay, so when you form this in this type of a condition, you don't normally stop here, because as soon as you form this here, right, and they are also one of the chemicals in the flask, so those radicals can run into this and create this intermediate by abstracting hydrogen from here, and that's very favorable. As you can see, if you abstract hydrogen there and you put radical there, and that radical has sort of you know, resonance style of stabilization, and also it has you know, secondary with the chlorine donating electron through a sigma bond. So this is quite stable, more stable than this. Therefore, as soon as you form this, it is more likely to form this rather than chlorine attack on the original propane and form propane radical, because this is more stable than this. So it happens more faster than this. Therefore, you're gonna end up having two chlorines, this compound. So if you aim to make this one, you have to check and monitor your reaction and stop where you need it to stop. Otherwise, you end up getting this more. So one of the last thing I have to talk about the radical mechanism is that when you use bromine and chlorine, they're quite like popular in organic synthesis because they are good leaving groups, and the alkane cannot react without leaving group. So in order to put on the leaving group, this is useful. If you want to put a more substituted carbon as a target, you use bromine. Well, if you want to put chlorine on the primary carbon, then chlorine is better. It's because chlorine is in general more reactive and the bromine is more selective for the more stable one. Bromine's preference for tertiary over primary is like a 1600 times, but chlorine for you know, preference is just a 5 to 1. So when you have a 9 primary hydrogens here, you know, chlorine goes for the primary because they're not so selective. The reason being, you know, when you break the bond, the bromine doesn't need as much energy to go up here, and then chlorine need a lot more energy. Okay, then as you saw before, this is the initiation step, how much energy is required. But when you enter the propagation step, when they attack primaries, secondary and tertiary, the radicals, the energy of the radical, okay, this represents the energy of radical, is in this order. For bromine, going to the tertiary is not too bad, but you know, secondary and primary requires few more kilocalories, and I mentioned before, couple kilocalorie makes the reaction favors like 85 to 95%. So tertiary is a lot more favored. But for chlorine, I mean, highly depends on the structure of these carbons, but simply speaking, primary is not too bad, secondary is good, tertiary is good. So for unstable chlorine, it doesn't really choose which one to react. It just go by the probability of where the chlorine is attacking. So when you have a 9 chances on the primary hydrogen versus 1 chance on the tertiary, it doesn't matter which is more stable for chlorine, because it is so reactive, so it can react with anybody in the comparison to the bromine. Still is the case, chlorine prefers tertiary, secondary, and primary, but the preference is only 1 to 4 to 5, simply speaking. But bromine is like a 1 to 1600, about 80 for a secondary times more. Secondary is more reactive. Then they go to a product with the exothermic, so it's not our concern. Those steps, initiation and especially propagation step, is the key in this selectivity and the reactivity. Finally, really briefly, because we're not going to do much of this soon, but all of the previous mechanisms, ionic, positive, negative, or the radical, they are stepwise reactions. And in some case we had a concerted reaction, like a substitution, but I haven't shown you the detail, which will be doing it soon. But when you deal with these double bonded compound, they can do sort of bringing 2 molecules together without forming any intermediate. Using their p orbital in the pi, they can share electron here and there, and they form this. You can even have, these pi itself, using internal interaction, they can go to ring structure like this. So these reactions comes way later, and I hope I can give you more detail, but this can be caused by heat or also light as well, depends on structure. Okay, before I wrap up, I have to give you a little idea about how to estimate stability. In previous beginning of this series of the videos, right, I gave you general idea. You estimate the potential energy to judge stability. Everything wants to be stable. If it's possible, it wants to be the most possible stable. And sometimes you have to judge, you cannot reach most stable state because of the activation energy is required too much. So kinetically it's forbidden, it's a slow. So you have to choose a lower activation process to form second best or third best and so on. But in general, when you judge the stability, even the product or the transitional state, you go by these 3. If you have negative charge on the bigger atom, it makes the potential energy lower and more stable, because negative charge means you have too much electrons. In terms of positive, it's okay to have a positive charge. It is stable. But stable doesn't mean it's not reactive. The positive charge itself, it may have a low potential energy, like in physics. However, it is attracting even small negative charge and causing reactions. So positive charge is reactive, but it's stable. So it also is the case when you have a more positive charge density, it is more attractive. So small atom having positive charge make it even more reactive than the big atom. for the positive. Resonance make the chemicals in general more stable, whether it's a positive or negative. In terms of negative ion, if you have a resonance, you are spreading negative charges over more atoms and bonding area. So you are diffusing the repulsion and it becomes more stable. When it's a positive, you are attracting electron from more flexible area like a pi bond lone pair. So those electrons in the pi or lone pair or even sigma for hyperconjugation, it tend to get more attraction by filling the positive ion that is attracting those electrons. So providing more positive charge to the electron, even the positive can be more stable in resonance. And also you want to put electrons, if it's possible, without going against these notations earlier, on the more electronegative atoms. So it's easier if you have to compare whether it's oxygen versus or carbon, nitrogen versus chlorine. They have a significant difference in the size or electronegativity. However, if you have to compare carbon to another carbon, then you have to get to the hybridization type. So sp3 is less electronegative carbon than sp carbon. So you like to put the negative charge on the sp carbon. But there are more situations you need to look at the structure. So let's see how you can lower potential energy. When you think of the carbon positive compared to other, a positive charge in some reaction, you need to choose where you want to put positive charge. It will happen in the substitution and elimination and the addition reactions and the rearrangement as well. So every single reaction you have cases where you need to consider where you want to have a positive charge on the carbon. So you're not comparing different size, you're not comparing different electronegativity, it appears, but sometimes it is the case. So when you look at the carbon with one carbon as a neighbor to the carbocation with a more neighboring carbon, that's when you have the situation where the more electrons can be donated from the neighboring carbon with the multiple carbon on it. So if these are the isomer with the same number of carbon and the hydrogen, then you can say this carbon with a charge is more stable. When you say that, we are not saying this carbon versus that carbon, we are saying this whole molecule versus this whole molecule. So why this is more stable? As you can see, the positive charge is attracting these more pairs of electrons and subsequently more pairs of electrons on the carbon. Therefore, having the plus charge in the middle of the molecule, you are stabilizing electron more by providing more electronegativity to all of the electrons. If you do that, when you have a multiple connections, you're only stabilizing the electrons around this area. Therefore, you have a less number of electrons getting stabilized, feeling the attraction weaker, so you don't go down as much. So this is more stable. Simply speaking, tertiary more stable than the primary carbocation. What about the primary carbocation with the special structure like this? Yes, it's primary. It is only stabilizing these electrons through the bond. That's induction, okay, inductively. But induction is not moving electron as good as resonance. As you can see, you can move this electron over here through resonance. If you had double bond there as well, then you can move the electron over here as well. You end up stabilizing all of these electrons. So even when the carbon is positive on the primary, it could be more stable even than the tertiary, depends on situation. So I want you to not just go by tertiary, secondary, primary in the order of stability from the most tertiary to the least the primary, but I want you to look at the structure and carefully judge by considering which way you are stabilizing more electron in the given situation. How about double bond? You can have double bond here versus here. Which one's more stable? So how do you go by that? I'm not gonna give you all list of the double bonds. You can find them easily online, but I'll give you the principle. The carbons you can see here with the double bond, they are sp2, and these carbons are sp3. And you all know sp2 is more electronegative, so electrons going this way and this way. Here, this sp3 is giving electron to the sp2 carbon here. So again, more electronegative two sp2 carbons stabilizing more electrons from the sp3 carbons and attached to atoms. Therefore, having more electronegative double bond carbons in the middle of the molecule is stabilizing overall molecule of the isomer more stable. In brief, double bond with more substitution compared to this, only one is more stable. But if you go by that again, you can fall into the mistake. So I rather go by the analysis like this, and then consider actually in the given structure, not this simple type of structure, but real structure, which is the case you stabilize more electron. How do you deal with the negative ions, you can ask. Again, I'm not trying to give you all lists and examples of this simple exercise, so I'll give you the principle. When you compare these two, yeah, this carbon is a secondary and that's a primary. And people can say, oh, methyl groups, electron donating groups giving more electron to this carbon, so this has a more electron density, not stable. You are right in the answer, but your explanation is not scientific. Because carbon with a negative charge is sp3. This carbon neutral is sp3. Here as well, all sp3 carbons. They're same sp3. However, this carbon has an extra electron, meaning on the second shell of the valence shell has extra electron, causing electrons repelling each other, so they are less electronegative. These are the more electronegative neutral sp3s. So they're not really donating. It's just a memorization that methyl is donating. Methyl donates to more electronegative atoms with sp2 or positive charge. So how do you explain this? You actually have to look at the hybridization in more detail. So what angle do you give for this carbon and the groups on this carbon? Let's pause and think about it. So this is the situation. You have the primary carbon ion with a certain angle between hydrogen and the methyl group, close to 110. But when you have two bigger methyl groups side by side, sterically they are more pushed apart, so you have a greater angle here. meaning you have a smaller angle between the methyl groups and the lone pair. So if you remember, if you go completely flat like this, the lone pair will be in the pure p orbitals. Okay? But when you compare these two, this is more closer to the flat. So what does that mean? Originally, the lone pair here is in the pure sp3 almost. But as you cause more repulsion, having secondary, one more methyl group or bigger group causing more repulsion, make them go away more from sp3. So it's going closer to the sp2, meaning this is going closer to the to the p orbitals. So which is more stable, electron in the sp3 or the lone pair in the p orbital? sp3 is more stable. So the electron in the p with a no s character, in this case it will have some s character, but not as much as sp3. So this is very unstable in high potential, so it is acting as a better base. That's why. It's not because methyl group is donating electron. So then you can compare that secondary to this secondary in the propane with a nearly, I mean, it's not really 60 degree, but you know, close to that. So what do you think of this electron compared to that? Which one is more basic? Obviously, when this is closer to 60, it's smaller angle than that, not 120 like these guys. So you have a more p character here, because p is like 90 degree, right? So you go away from 109 hybridized to the smaller angle, you give more p character here. Meaning in the mixing you put more s, less p for this electron pair. So the electron becomes more stable in this secondary. So this is more unstable. Therefore, among the secondary, that's more reactive. So instead of making a long, lengthy video about the intermediate and their stability here, I'm going to touch upon these things whenever the issue arises, when I deal with the certain reactions and mechanisms. But please try to understand general idea how you go by you know, for stability of any compound, including intermediate